Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Identify the compound. The structure shown is 1,2,4,5 tetramethylcyclohex 2Na, or equivalently described as a cyclohexene with methyl groups at 4 positions. Looking carefully at the structure, there is a 6-membered ring with 1 double bond and 4 methyl groups. The double bond carbons, C1 and C2 say, each bear 1 methyl group. These are sp2 carbons and are not stereocenters. The remaining 2 sp3 carbons bearing methyl groups, C4 and C5 or whichever 2 saturated carbons carry methyls, are the potential stereocenters. Moving on to the next step. Identify stereocenters. Only the 2 sp3 ring carbons that each carry a methyl group are potential stereocenters. The sp2 double bond carbons cannot be stereocenters. So we have 2 stereocenters. Moving on to the next step. Apply the 2n formula cautiously. With n is equal to 2 stereocenters, the maximum number of stereoisomers is equal to 2 is equal to 4. However, we must check for mesoforms due to molecular symmetry. And for the final step, check for symmetry mesocompounds. The molecule has a plane of symmetry consideration. With the double bond fixed in the ring and the 2 sp3 methyl-bearing carbons, we need to enumerate R, R, S, S, R, S and S, R. Due to the symmetry of the ring, the 2 stereocenters are related by the plane of symmetry passing through the double bond midpoint and the opposite bond. The R, S and S, R configurations represent the same mesocompound. So, R, S is equal to S, R is equal to 1 mesocompound, R, R is equal to 1 enantiomer, S, S is equal to 1 enantiomer. R, R, S, S as 1 enantiomeric pair and 1 mesoform. Total is equal to 3 stereoisomers. Why other options fail? Option A, 2 is wrong because it ignores the mesoform. Options C, 32 and D, 64 are vastly too large. They would require 5 or 6 stereocenters, which this molecule does not have. Therefore, the correct answer is B. Therefore, the correct answer is option B.